All right, let's dive right in. Today, we're exploring the really elegant, almost magical relationship between waves and how they change moment to moment. We're talking about the calculus behind trigonometric derivatives.
So let's just start by looking at this. It's pretty incredible. If you take a sine wave and you trace its slope at every single point, how steep is it right now? The pattern you draw ends up being a perfect cosine wave. When the sine wave is climbing fastest, the cosine wave is at its peak. When the sine wave flattens out its crest, the cosine wave hits 0. This is way too perfect to be a coincidence.
And it's not a coincidence. It's actually a fundamental property of how these functions work. But why? Why does measuring the slope of a sine wave, point by point, trace out a perfect cosine wave? That's the mystery we're going to solve. To really crack this code, we can't just trust our eyes. We have to break out the foundational tools of calculus.
And this right here is our master tool, the limit definition of a derivative. Now, I know it looks a little intimidating, but the idea is actually pretty simple. All it says is this: to find the slope at an exact point, just pick another point that's incredibly close to it. Then measure the slope of the tiny line between them and see what number that slope approaches as the distance h shrinks down to basically 0.
Now, before we plug our sine function into that formula, we need to gather our ingredients. There are 3 specific tools we need from our calculus toolkit: a key trigonometric identity and 2 what we call special limits that have already been proven. These 3 pieces are absolutely essential.
Okay, so let's watch how this all comes together. In step 1, we just put sine of x into the limit definition. Easy enough. For step 2, we use that trig identity we just grabbed to expand the first term. Now, it looks a bit messy, I'll admit, but step 3 is where the magic happens. We just rearrange the pieces to isolate those 2 special limits we gathered. See how they're perfectly lined up? And finally, in step 4, we apply the limits. The first part goes to 0, the second part becomes 1, and after everything cancels out, all we're left with is cos of x.
And just like that, the math confirms exactly what our eyes suspected. The derivative of the sine function is the cosine function. That visual pattern wasn't just a neat coincidence, it is a mathematical certainty. So here's the crucial part. We've just knocked over the first, most important domino. Because we've proved the derivative for sine, and we can use a really similar proof for cosine, we can now figure out the rules for all the other trigonometric functions. These 2 rules you see here, they are the master keys. The fact that the derivative of sine is cosine and the derivative of cosine is negative sine. With just these 2, we can unlock everything else. So how do we do that? Well, take the tangent function. We all know that tan x is just sine of x divided by cos of x. And since we now know the derivatives of the top part and the bottom part, we can just use a standard tool, the quotient rule, to find the derivative of the whole thing. By applying rules like that one to our 2 master keys, we can quickly build out this entire set of 6 derivatives. What we end up with is a complete toolkit for the calculus of any trig function you can think of. Okay, this is all great, but it's not just some abstract math puzzle. This is the actual language that physicists use to describe anything that oscillates or moves in waves. Like a weight on a spring or a pendulum swinging back and forth. It's the math of simple harmonic motion. Let's make this real. Imagine a tiny particle moving back and forth, and its exact position at any given time t is described by this function right here. So a key question in physics would be, when does this particle stop moving, even for just an instant? In other words, at what times is the particle at rest? To figure that out, we have to find out when its velocity is 0. And in the world of calculus, velocity is just the derivative of position. So we take the derivative of our function s of t, the derivative of 2 sine of t is 2 cos of t, and the derivative of negative t is just negative 1. And that gives us our velocity function. Now the problem becomes much, much simpler. To find out when the particle is at rest, we just set this velocity function equal to 0 and solve for the time t. And when we solve that equation, we find 2 specific moments in time, pi over 3 and 5 pi over 3. Those are the exact instances when our particle stops and changes direction. All of that just from knowing the derivative of sine. But you know what? The story doesn't even end with velocity. What happens if we just keep taking derivatives? The first derivative is velocity, the second is acceleration, the third is called jerk. What pattern emerges if we keep going? Well, if we start with sine and keep going, something amazing happens. You go from sine of x to cos of x, then to negative sine of x, then to negative cos of x, and on the fourth step, you land right back where you started, at sine of x. It's a perfect, repeating, four-step cycle. This cycle means that every fourth derivative of sine is just sine again. It's an infinitely repeating pattern, and that predictability is incredibly powerful. If I asked you to find the 74th derivative, you wouldn't have to do it 74 times. You just figure out where 74 falls in that four-step cycle. In this case, it's the same as the second derivative, negative sine of x.
And this really brings us full circle. We started with just a visual pattern we saw in a graph. We used the tools of calculus to prove it was real. We applied it to a physics problem. And then we discovered an even deeper, infinite pattern hidden inside. It really makes you wonder, what other elegant mathematical patterns are hiding all around us, just waiting in plain sight?